Very basic computer science fundamental concepts took 1.8 second, just 1.8 second to sort 10 raised to power 7 elements on MacBook M1 Pro, like 8 cores, 8 threads. Hello everyone, welcome in our new video of applied computer science. And let me tell you a story. So basically last weekend when I was getting bored, I was thinking about implementing something so that I would be able to think more. I would be able to use more brain power, right? So last weekend it was like, what can be done apart from making chat apps, Uber clones, YouTube clones, right? So after a lot of thinking, or I should say overthinking, I came to the conclusion that why not to switch basics and add some masala to it, right? So let me set the context for today's video. So basically today we'll be doing something more crack version of computer science, where we will be using some basics of our data structures and algorithm and tweaking it, or I should say putting it to steroids, right? So a very basic thing that we use in our most of the DSA questions is sorting, right? Solving questions by sorting, be it quick sort, merge sort, selection sort, insertion sort. So let me take you to the screen and then I will explain you what we are gonna do today, and we'll code end-to-end project, we'll benchmark it, and you will get to know a lot of things. So let's start the video. So here is the plan. So basically whenever we start DSA, right, there is a plan of solving questions, which is there is a set of instructions that goes through our mind, right? Ki think about sorting, right? Think about sorting. If your question can be solved by sorting or not, think about it. And most of the people might know that n log n is the computing power, or the computing power that our algorithm, basically sorting algorithm, takes, right? And most of the important, or I should say famous algorithms are quick sort and merge sort. It's not because they are fast, it's because their implementation is highly recursive. I should say ki whenever someone starts a project, or I should say DSA, the most fascinating thing is recursion, backtracking, and dynamic programming, right? So I was thinking last weekend, why not to mix recursion with multithreading, because both are computer science fundamentals only, right? There is no React framework, Angular framework, Spring Boot involved in this, just plain computing, just plain computing the instructions, right? So why not to explore this? So what this video is about, we will be exploring merge sort, right? We will be sorting 10 raised to power 7 numbers in an array using merge sort, which will take n log n kind of computing power of our PC, right? So I am using Mac M1 Pro. Yeah, that's the machine that I am using. So then we will be trying to change this algorithm, or we'll be tweaking this algorithm to parallel merge sort. I'll explain you how that will work after explaining you the merge sort, obviously, for the people who don't know. So we will be using recursion plus multithreading. Trust me, it's gonna be so much fun. Okay, do watch the video from start to end. It will be it will be a value bomb, I would say. Okay, so before jumping to the code, before starting up the project, let's discuss about what exactly is the merge sort. So basically, let's say you have an array, right? You have an array. So I would just basically give you an example of 5-7 elements, whatever. Okay, so let's say you have an array where one number is 5, another number is, let's say, 10 maybe, third number is 2, another one is, let's say, 1, another one is, let's say, 20, then it's 10 again, right? Then it's, I would say, maybe 0, right? So this is an array. So let's take this array as an example and we'll try to sort this out. So merge sort, what merge sort does, merge sort is a divide and conquer algorithm, right? What it does is it takes 2 pointers. First pointer is low pointer, second pointer is high pointer, basically the left and right pointer, right? Then it calculates the mid. right? Whatever the mid is, either you can take lower bound mid or you can take the upper mid here, whatever. So whatever the mid is 0, so the indexing is 0, 1, 2, 3, 4, 5, 6, right? So 6 divided by 2, 3, 0, 1, 2, 3. So the mid will be exactly in the middle. So then you will divide these arrays, right? You will divide these arrays. So you will be dividing this array into 2 arrays so that you can divide this array, and then iteratively, or I should say recursively, you will sort the smaller arrays, right? So now few elements will be in this array, okay, from low to mid, and few elements from mid plus 1 to high. Like this pointer array is the left array, right? Left array, and there is the right array. Still both are unsorted. We will be dividing these arrays, right? We will continue to divide these arrays till we get one element, right? Then again half this array, divide these arrays into 2 array, right? Again we'll divide these array, okay? So yeah, this process will carry out. Then again divide this array and so on, right? Similarly for this. So at some point we'll get 2 elements only, like one element here, one element here, and as you guys can guess that those 2 elements will be 5 and 10, right? 5 and 10. So single elements are, you know, eventually sorted arrays, right? There is no other element, so ideally this left array is sorted array, this right array is sorted array. So in recursion we have a basic, you know, process which is keep doing it until you meet a base case. When you meet a base case, backtrack from that point. So here our base case is when your left is more than equal to right, right? So, or you can say only one element is there in the array. So at that base case we can assume both are a sorted array. What we'll try to do, we'll make a new array of size 2, right? We'll make a new array of size 2. We'll take 2 pointers. We'll take left pointer, we'll take right pointer. We'll check if left element is less than right. If yes, we'll put left element here. Otherwise, if right element is less than left element, we'll put right element first, right? So here we'll put left element first, 5, then here we will put 10. So then this array, we will return this array as the result of our base case. This is our base case, we combine the base case, we return it, right? So this is the result. Similarly, there would be another 2 elements which will be like 2 and 1 here, 2 and 1, some right array 2 and 1. We'll combine them here. What we'll do, we'll make a array, right? We'll make a array. So we'll check if left element is smaller than the right element. No. So right element is the smaller than left element. So we'll put 1 here and we'll put 2 here, right? So this is the sorted array. We'll return this sorted array as the result of our base case. So now we are backtracking from our base cases. Just remove it. Okay. So now what you can say is these both arrays are sorted array. So whenever you are backtracking from the bottom, you can just assume whatever the result you are getting from the, you know, downward direction, those arrays you will always get in sorted order. So now what you have to do, you have to initialize a pointer here, left pointer, right pointer. As both arrays are sorted, you just have to make an array of 4 size, right? 4 size, and just check if left is less than right. No, right is lesser than left. Put 1 here. Progress this pointer. Now check 5 is less than 2. No, 2 is less than 5. Put here. Progress this pointer. This array is empty now, and there is another loop which will take this 5 here, because there is no element left in the right array to compare. Just put all the elements that are left in either left array or right array. So this is the result of these 2 arrays combination, right? These 2 array combination result is this. We'll return this to upper step. Upper step will again use this one, and upper step will use another array from its right part. So basically what we are doing is we are just starting from here, right? We are going downwards with smaller circle, right? Smaller circle. We are continuing its process until we are meeting a base case, which is normal circle, right? Then we are using those base cases, using these base cases to return something, right? So we are using the base cases here to return something here, right? Similarly here, and eventually we are going top to bottom, then bottom to top. This is the recursion, right? So if it seems complex, just go and watch the visualization of merge sort, any video. You will be able to understand most part of it, right? So I hope a basic understanding of merge sort you got. Let's implement the merge sort, but before that I would just give you a glimpse how we are able to like achieve a very good performance of about 20 times better performance in parallel merge sort. What we'll do is, whenever we are starting up two process, we go to one array, we are starting up two steps here. First step is here, like sort this array first, right? Sort this array first. So from this function we are basically making two more function, right? But this is sequential. If you will see, recursion is always sequential. This array, left part of the array, this array is going into the left direction, this array of the right part is going into the right direction, right? But see, both of these parts are independent. I can sort my left array independently of right array. If both parts are different, why can't I use my CPU power? I have 8 cores in my MacBook. Why don't I use it, right? So let's use our CPU cores, 8 threads, and let's sort this in more efficient way. So what I can do is, while spinning up a new function in left, I will spin this function in a separate thread. Sorry for the spellings, but anyways, and this will be the separate thread. So basically two threads are there, right? Two threads are there from main function T1 and T2, right? We'll allow T1 T2 to perform their operation without acquiring any lock, any mutex lock. Why? Because both are independent. They are not accessing any common part of the array. They are performing their operations on the different parts, so it's okay, right? So again, T1 will spin more thread, maybe T1 dash, I don't know, and T2 dash, right? And in every step of recursion, we will perform that recursion in separate thread. And the thing is, at one point in time, when we will try to sort 10 raised to the power 7 elements, like array having size equal to 10 raised to the power 7 elements, it will exhaust our resources, and you will see that we are getting error like resources are insufficient. So there we will be using a thread pool. What a thread pool is, will allow only a set of threads to perform function. Let's say my CPU is, I will basically do hit and trial. I will see if I can spin all the threads. If not, I will bottleneck my performance. I would say ki spin up to 10,000 thread or 1,000 thread, right? Spin up to 1,000 thread. Let's say till this point I have I spun up 1,000 threads till this point, right? And my CPU can handle 1,000 threads at a time. That I know, right? That we will see in the code. Now from this point further on, what I will do, I will do this in simple recursive step. I will not spin more threads because all of my resources are consumed till this point, right? So we'll perform simple sorting and log n if our thread pools got exhausted or if our resources got exhausted. So the resources, the number of threads that you can spin can differ in your computer, can differ according to your machine. That is perfectly fine. So let's get to the implementation. Let's get to the item. So I will make directory here, multi-threaded merge sort, right? Let's open up our IDE. Let's make a folder here. We'll always follow src app nomenclature, as you guys already know. In most of our videos we follow this structure only. So let's start it, right, without any further ado. So let's make a file, merge sort.hpp. We'll make header file first. It is necessary whenever you are working with multi-file C++ project. So simple, if not defined merge sort header file, like include header file only once. That's the usage of this directive, merge sort header file. And we will include vector. Vector is basically dynamic array, or if not defined. So here what we'll do is we'll make a call class merge sort And this is the normal merge sort implementation, not any rocket science. So we'll initialize an vector here with like vector pointer. Basically it will be, you know, it will point to some vector that will pass from main function. Fine. Then let's make some public. Okay, let's make some public function. First function is normal constructor that will take vector. Okay, vector of type int numbers, right? Then we'll make a destructor which will do nothing as of now, and we are just declaring our function, right? We're not giving any implementation. Recursive sort, this will accept 2 pointers, int left, int right, and that's it, right? That's it. And let's close this class. And if, right, now let's make a folder sorting. Let's put it here, move in sorting, and let's make a main file here, main.cpp, from where we'll be passing some code, right? So in merge sort, let's make a C++ file now, merge sort.cpp. Here what we'll doing is we'll be just using the, you know, merge sort algorithm. So we'll include our parallel merge, okay, not merge sort only as of now, merge sort.hpp, and we'll be just using the function that we have declared and provide its implementation. So in instructor we'll just do, so in constructor it will just get some numbers and initialize the variable that we have here, right? And merge sort, this will be empty, we'll not be doing anything. So here we'll write recursive sort algorithm. Okay, this recursive sort will write it later. First let's write you know, normal function, which is a very small function, void merge sort and sort. What it will do, it will check if, will dereference the pointer first, and will check if that array of numbers that we have initialized in our constructor, its size is 0, then return from here only, return or exit, whatever, right? If not, then run recursive sort algorithm, right? Just pass left as 0, start from 0, and the rightmost will be the, you know, the maximum length of the array, right? So let's dereference the pointer, which will dereference to vector, and then find the size, then recursive sort will go here only, right? Let's write the algorithm of recursive sort. So the base case is whenever your left pointer becomes equal to right pointer, just return from that step, and if not, find your mid, which is left into left plus right minus left divided by 2. This is how you can find mid. Now the thing is, you can find mid just by right minus left divided by 2 also, right? But the thing is, the integers, like there is a value of integer that is bound, right, according to the number of bytes that integer can use to you know, store your integer. So is it a long integer, is it a simple integer? So that depends. Just because of that, we are just subtracting first, then adding it up, right? So but anyways, it will also give you a mid only. We'll again call left and right until we don't reach to our base case, right? So straight away we'll call left and mid, and recursive sort of mid plus 1 and right. That's it. That's it, right? Now we'll keep calling it, we'll keep calling this function until this base case hits. Whenever this base case hits, we'll come here, right? Now what we'll do, we'll make a vector, right? We have to, we have left vector, we have right vector, we will compare them both and we'll store those values in some vector, right? So we'll have to make some resulting vector, right? Let's initialize some temp variables. Let's start I from left and j from mid plus 1, right? And just keep this implementation int, sorry, I is less than equal to mid and j is less than equal to right. So basically we are performing the left right iteration on two different arrays, right? So what we'll do is we're not dividing the array, we are sending the I and j. Basically what we are doing is, okay, we are just making this I and j smaller, right? In next step we'll make this left equal to left and right equal to mid, and similarly in the right part we'll make I equal to, or I should say left equal to mid plus 1 and right equal to right. That's what we are doing here, right? Here. So we are just dividing the parts using pointers, I would say, index. So yeah, that's there. So let's check if left part is less than equals to right part, then you just have to do result dot pushback, because left part is smaller, so put left number into the resulting vector and just increment that vector, right? Otherwise if it is not less, obviously the other part would go, which is this stuff, numbers, and here j, and just progress your pointer here. So yeah, that's it. So whenever this will exhaust, we saw earlier that some vector, let's say right vector, might be all of the elements of right vector might go in resulting vector, right? And there are some elements left in the left vector, right? And the other way around, obviously. So yeah, that is there. So because of that we have to perform some other operation, and this is the normal merge sort algorithm. Okay, I'm just explaining too much, I feel. So this is just to make sure that no vector is left, right? We have to push back all the elements, and as left and right part are sorted, obviously because of our base case we assumed, so that's why we can always assume whatever the elements left in right or left vector will always be in sorted order, and that is a true assumption that we saw, right? So if j is less than equal to right, result dot push back, you just have to push back numbers j, right? And increment the j. So whoever the vector is there and is not empty, we are just pushing that back to our result vector, and we are just now making sure that whatever our result vector we formed, we are just making it sure that we copy all of the result vector k elements in our numbers. So it is now we are just replacing all the numbers from our result vector which are already in sorted manner and just return from here. This is the merge sort algorithm, and that's it. Why this is okay, the problem is here, we have to dereference it first and then use it, like use the indexing. So that is the merge sort, right? Should we write merge sort, like should we use this merge sort first? Let's use this, include IO stream, right? And include sorting merge sort.hpp int main. Let's make a main function, int argument count and character array argc, right? Okay, no, arg v. Okay, so what we have to do is we just have to do int size, right? Let's take 1000 elements first. We'll benchmark our algorithm on 10 raised power 7 elements also, don't worry. So we are just making a number, right? What the fuck is this? Okay, so for now on, let's make int I is equals to 0, I less than size, and I plus plus. And then what we have to do is numbers I is equals to random integer divide by 1000. That's it. Okay, let's construct this array first, right? Random vector, then merge sort, right? Merge sort, let's take merge sort and use merge sort new, and it will return us the pointer to the merge sort instance का memory. ठीक है? So here we have to provide the address of the numbers because merge sort is accepting the address. Start is equals to chrono is just time library, right? High resolution clock, we are just making sure that what is the current time, right? We have to make sure like the time taken by this merge sort algorithm, right? So that's what we have to merge sort. So sort your elements, and auto end is equals to, okay, that's it. Std chrono duration double this. Okay, so here what we are doing is we are just printing out the time count, and that's it, right? That's it. This is the merge sort algorithm ka time, and last we have to delete merge sort ka pointer because we have to delete it, right? The memory that is allocated by this instance. So I think that's it, right? That's it. Let's run it. Okay, I have the whole stuff here. We have not implemented parallel merge sort yet, right? But I will copy this command to somewhere else. Okay, so let's remove this parallel merge sort and pthread because we are not using the threading library as of now, right? We are just using the merge sort. No such file main.cpp. Why? Okay, src app. Okay, so let's run parallel sort. Time taken is way too less. Okay, way too less because only 1000 numbers are there anyways. But if you want to print the vector, that also we can do whenever we are recursive sorting it. Then what we can do is for int I is equals to 0, I less than dereference the numbers dot size, and I plus plus c out, and just dereference the numbers and print it std and right. And here you have to include IO stream. I think that should be okay. Yeah, let's compile it again, run it. Okay, what is it print? Okay, let's not do it. We have to make sure that our algorithm is working. Okay, and it's not working. It's not working. Let's dig down deeper. Merge sort, left plus right minus left, recursive sort, vector mid plus 1. What can go wrong? Type in the comments what can go wrong. I is less than equal to mid. I is less than equal to mid numbers. I think it should be okay. Okay, very silly mistake, dumb mistake. If left is more than equal to right, we should return. This should be our base case, not the other way around. Very dumb mistake. Yeah, now it should work, right? Sorting, you are getting the sorted array of 10 elements and you are like way too less time, right? Let's implement our parallel merge sort first, and then we'll compare the timings of parallel merge sort and our normal merge sort. Parallel merge sort dot hpp. So I will just paste the things here for declarations, because there is no code involved here for regarding any multi-threading and all. So we are just using parallel merge sort here. Vector, again similar to our merge sort, everything is similar, right? Just let's jump straight to parallel merge sort dot cpp, and we will include some of the stuff here. Include parallel merge sort dot hpp, and again the constructor is same. You are just using the numbers, and here you are in like declaring the numbers in line, right? You are not using this numbers equal to numbers, and it's also fine. And the algorithm of merge sort will be same. The recursive sort algorithm will still be the same, right? That is same. The thing is, when we are calling the left and right arrays, that would be different. Like you are spinning up a thread and then calling them, right? So I will explain you the whole part here. So this is the parallel merge sort recursive algorithm, right? What is this threshold? Skip this, right? Okay, now left is more than equal to right, return. Same thing, same left. Now skip this thing. The whole stuff here is similar to the normal merge sort, right? Normal merge sort, and this is also normal merge sort, right? So let me put back to normal merge sort here, and this is our normal merge sort. Now what we'll do, whenever we are calling this recursive sort, we have to call them in different thread. And in thread model, like in threading model, what we have to do is include, either you can include threading model here or in the hpp file, both are fine, and include iostream, CLUDE, include iostream also. So here what you have to do is, whenever you are calling this recursive sort, you have to call them in different thread. And to make that thread, let's make that in another line, std thread1, right? And you have to accept here this instance of class, because you have to pass the context of this instance of class to another thread, right? So then you have to call this dot recursive sort left to mid, that is your thread 1. And similarly you can spin up the second thread using lambda function. Here in lambda you're accepting this, right, mid and right, and here you will pass mid plus 1. In lambda you have to accept them. You can't use the variables declared here, right? You have to pass the context also with the variables that you want to use in the function in the thread, right? So this is how the process is to spin up few threads. Now you have to join the threads also, because you have to wait for the left part of the array and right part of the array to run, right? So you have to use thread1 dot join, which will wait for both the threads to complete their part, and both the threads can run in parallel. That is the thing, left and right will run in parallel, and in every recursive step 2 threads will be spinning up per parent. Like whenever parent is spinning up child, it will spin up the child in different threads. Then a hell lot of threads will be there whenever you are sorting a huge amount of numbers, right? So the thing is, you are running the left and right part in parallel, and they are both independent. That's why there is no need to acquire any global lock, right? So this is there. That is how you are spinning up the thread. And the main function of sorting function that we have to declare is void parallel merge sort parallel merge sort, spelling correct. Okay, if again the dump condition is here, the numbers dot size equals to 0, then just return, no need to do anything, right? But if it's not, then spin a thread, right? There is no need to spin a thread here also. I'm just doing it because I have some kind of chul, right? This recursive sort and 0 numbers dot size -1, just do it like this, and thread1 dot join. Yeah, that's it. That is the parallel merge sort, right? We have not implemented. I told you there could be an exhaustion of thread pool, like the number of threads running at a time on your computer may get exhaust, right? So that we'll see anyways. But we have just to create, another numbers. Let's create numbers one array, right? And here let's put those numbers here, so that that thing will pass to parallel merge sort, right? Here what you will do, parallel merge sort. Okay, you have to include that first. Okay, so parallel merge sort you have to include, and then here you have to make sure that you are calling up the parallel merge sort, and do it merge sort 1 because merge sort is already declared there, and do it maybe don't declare it again, just initialize it here, and here you have make sure merge sort 1, and merge sort duration here you have to declare only, like define that, and here parallel merge sort took time, and here delete the parallel merge sort, no, merge sort 1. I think that should be fine, maybe not. Let's print the elements. You just have to copy this function and put it here. If you want to be a good programmer, just make sure you know how to copy paste. Okay, everything is fine. Now the second command will get used, right? Why? Because whenever you are using C++, you have to make sure that you are linking up the another libraries which are not present in your current project. So you have to link pthread library here, right? Okay, note this thing. Okay, whatever. One error generated, file not found, parallel merge sort, parallel merge sort.hpp. Let's rename it, copy this. Okay, you have to make sure that you are including it in, I think this maybe, yes, that's how you have to use that. Okay, now what it is saying is ki parallel merge sort pthread undefined symbols for architect referenced from main link. Okay, what the fuck is this? CPP. Okay, parallel merge sort, right? And you have to do this and declare this. Now let's do this. Okay, now it's fine, and parallel merge sort. Now the merge sort algorithm, right? Our normal merge sort algorithm took 10 raised to power -4 maybe, and this took, I don't know, right? So both sorting are working, right? Let's make it a real fun. now you have to remove this printing stuff, otherwise your terminal session may get crash. So just remove this stuff here, just remove this. Okay, now let's compile this program again. Parallel sort. Okay, whatever the time is there, I don't know. So this is taking too much time according to you, right? Now let's shift this to, because 10 numbers are very less, right? 10,000. Okay, so now let's test this. I have commented everything here, and I've done everything, right? You will get the link in description, right? So here I am putting up 1 2 3 4 5 6 7 10 raised to power 7 numbers, right? Mostly the merge sort algorithms get crashed at this point, but one more thing I have added, but before I will remove that thing first. Let's comment this thing first. Okay, and let's go to terminal. Okay, parallel sort. Now the normal merge sort will run, but the parallel merge sort will give you some error because I'm not using up any limit to spin up the threads. Let's wait. You have to wait for a lot of time because 10 raised to 7 number is a huge number for CPU to process. Usually CPU is able to process 10 raised to 6 instructions, like number of elements. So normal merge sort took 23 seconds, and parallel merge sort is giving terminating due to uncaught exception, thread constructor resource temporarily unavailable. Means our thread spinning up the thread, hardware threads are not possible anymore. So what I have to do, I have to make sure that I put some threshold. So basically whenever I am done with spinning up 5,000 threads at a time, I will check like if the number of elements right to left, the number of elements in an array are less than threshold, then that array size is very less, right? Their multi-threading will not make any sense. So I will not spinning up more thread. I will just use the inbuilt sort function to sort that part which is having size less than equal to 5,000 elements, right? Because their spinning up threads and everything is not efficient. So they just use n log n simple algorithm. So that's how we will be restricting ourselves to spin up the threads where the array size is huge. So there only we are using up the resources. So after doing this, let's parallel sort. Okay, so the difference is huge. That's what I was talking about. Merge sort took 23 seconds to sort 10 raised to power 7 elements, and our parallel merge sort with recursion, with multi-threading, using our very basic computer science fundamental concepts, took 1.8 seconds, just 1.8 seconds to sort 10 raised to power 7 elements on MacBook M1 Pro, like 8 cores, 8 threads, right? So that is the beauty of CS, and that is it for today. I hope you have learned a lot of things. If yes, tweet on the Twitter to tag me you can tag me @alpha decode x, right? So that we will be able to know that you are learning from our videos. Till then, bye bye.